Hello and welcome to the Genoa-Oceola Wastewater Treatment Plant. My name is Greg Teixeira, Utility Director for this facility. We'd like to welcome you on a tour of our facility today, and as we go through that tour, we'd like to discuss some design considerations for wastewater engineering in the future. Some of the items that we'd like to focus on is handling extreme weather events, dealing with recalcitrant and bioaccumulative chemicals such as PFAS and mercury, handling biosolids and residual management, which is becoming more and more difficult by the day, and also dealing with energy usage and the cost of energy in the future, becoming more efficient to lower your operational costs. The sources of wastewater for our facility include homes, industries, and commercial businesses such as restaurants. As wastewater leaves your home, it is conveyed to our facility through a series of collection system devices that we'd like to highlight some of the key design considerations for. First is a manhole. In looking at design considerations for manholes, we like to look at preventing inflow and infiltration, such as watertight covers, lining to prevent hydrogen sulfide corrosion of the concrete, as well as prevent infiltration, and also worker safety, looking at the placement of manholes in green belts rather than the center roadways, and then also looking at proper steps and ability to access the manhole without traffic. From manholes and pipes, wastewater then enters sanitary sewer lift stations, which function to raise the water from a lower elevation to a higher elevation. Key design considerations in designing and constructing a sanitary lift station include installing standby power to power the station in the event of a power outage and keep the wastewater flowing to prevent sanitary sewer overflow events. Constructing the station of sufficient size, volume, and elevation so that during peak storm events, wastewater can still be conveyed and not overflow, resulting in sanitary sewer backups into homes. Location and access adjacent to homes and businesses. It's important to install odor control devices so that the stations do not become obnoxious to neighbors with odors coming from them. Installing bypass connections, such that should power or actual pump failure occur, there's still an ability to bring a temporary pump in and pump the wastewater, again to prevent sanitary sewer backups into homes or the environment. And finally, installing remote monitoring, which will allow the operators to be notified in the event of high water, power outage, or other events to quickly react to prevent releases of sanitary sewer into either homes or the environment. In addition, you'll notice this station has pink lining, once again installed to prevent hydrogen sulfide corrosion from the wastewater of the concrete structure. Following conveyance of the wastewater to our facility through pipes, pump stations, and manholes, it reaches our headworks building. The headworks building's primary function is to screen the wastewater of all recalcitrant debris and to prepare it for biological nutrient removal through our biological treatment processes. Key design considerations at a headworks building are A, constructing a fine screen that operates by level control. This way, this screen is only running and consuming power when elevation reaches a certain point. Having the screen of small enough material, this one here is 3 millimeters in diameter, so that small material does not impact mechanical processes in the facility. Having accurate flow measurement, so that we're able to accurately determine the flow coming into our facility for calculating fluid to mass ratios, as well as regulatory reporting to the state. Odor control, this is one of the most odoriferous portions of a wastewater treatment plant, and we didn't want those odors affecting our nearby residents and property owners. Having redundancy, such that should the mechanical screen fail, we have a way to convey wastewater through the headworks building and still result in biological treatment. As well as corrosion protection. The wastewater coming in here is quite aged and typically has a pretty high hydrogen sulfide concentration. You'll again see the peak lining material that we've applied to our concrete to prevent corrosion of the concrete structures. These are all key items to consider in designing a headworks building. From our headworks building, wastewater is transferred to an equalization tank underground. From this EQ tank, we have 2 pipes emanating that allow us to split flow between our 2 oxidation ditch biological nutrient removal structures. In this way, we can either split flow 50-50 between the 2 devices, or provide more flow to one oxidation ditch or more to another, and it provides our operators the greatest flexibility in controlling flow between the two biological treatment devices. One of the key design considerations for any engineer in developing a wastewater treatment plant is to provide operational personnel with as many flexibilities as possible to handle all the different events that occur in wastewater treatment. From our flow structure, our wastewater enters our oxidation ditch. The first step in our oxidation ditch is called the selector basin. The selector basin aids in biological nutrient removal, allowing us to use much less chemical to conduct the removal of phosphorus, a key nutrient in wastewater removal. Wastewater is introduced with return-activated sludge in a very anoxic environment, resulting in the bacteria releasing phosphorus under this condition. And then as we reach through high oxygen at the end of the process, the phosphorus is uptaken, removing it from the wastewater and meeting our permit limits for discharge to the receiving stream. One of the key design considerations in any oxidation process for our biological nutrient removal, as well as BOD removal, is low energy usage. Oxidation ditches provide good oxygen delivery at relatively low energy costs compared to force-driven air or fine bubble diffuser systems. Other key design considerations for biological removal include chemical addition, having the ability to add chemicals such as ferric chloride or aluminum sulfate to precipitate phosphorus from the stream, or also possibly polymer to help in the settling of biological solids. Having sufficient hydraulic capacity to handle storm events and surges that occur during large storm events. Having efficient oxygen delivery. Again, our oxidation ditch here uses rotors, which is a very efficient process and results in lower energy costs for us, while providing efficient oxygen delivery into the water, as well as sufficient mixing. One of the other key things that we've added to our oxidation ditch system is meters that allow operators to quickly see redox potential as well as oxygen concentrations in each of the treatment trains in the oxidation ditch. In this way, operators can adjust the level, change oxygen conditions to provide the most efficient removal of BOD, ammonia, and phosphorus from the waste stream as part of the biological treatment process. Following the oxidation treatment process, wastewater then enters our final effluent clarifiers. Some of the key design considerations for final effluent clarifiers are sufficient hydraulic capacity to handle storm surges, efficient rotary scraping of the surface as well as the bottom for low energy usage, installation of covers over the final effluent weirs, keeping these free of algae and other growth of biological material, which reduces labor of our staff as well as allows for even overflow throughout the final clarifier. In addition, the scraper arm should have a scum beach on it to allow for the collection of grease and other recalcitrant compounds off the surface, which are then transported through the gravity system back to our headworks building for further treatment again through the process. Sludge that's collected at the bottom of the clarifiers goes into our return activated sludge building. Here a portion is either returned back into the oxidation treatment process or wasted to allow for proper population growth and control of microorganisms relative to the food that's coming in the wastewater treatment stream. In our building, we use 3 different types of pumps for redundancy as well as different flow rates to allow operators, again, the most flexibility in controlling the return activated sludge rates and the wasting rates for the best biological treatment of the wastewater. From the final effluent clarifiers, waste activated sludge is transferred to sludge storage tanks. From here it is pumped through a screw press, which thickens the sludge to a consistency of about 21% solids. Here it is put into dumpsters and transferred to a landfill. Our facility used to use a land disposal of biosolids. However, due to the stigma associated with this became difficult, as well as the variability of conditions such as crops, soil moisture, and trucking became more and more costly for us. This provides a much more efficient disposal of our biological solids from our facility. Eventually, our facility would like to look at going to a Class A biosolid where this material could possibly be utilized again for fertilizer or reuse rather than disposal in a landfill. Effluent water overflowing the weirs in the clarifier is then transferred to our tertiary treatment process. Our facility uses aquarobics final effluent filters. This is a disc design where wastewater filters through a fabric material and then transfers to the final UV disinfection. Material is then vacuumed off that collects on the filters by pumps and transferred to the headworks of the building for retreatment. This is a very efficient method of conducting final effluent filtering and provides good phosphorus removal in the event that biological removal is not sufficient to meet our final effluent limits. From the final effluent filters, wastewater is then transferred through UV disinfection banks. The UV disinfection process is again very energy efficient and much safer than using chlorine or other methods of disinfection. Operators must keep a key eye though to make sure that bulb intensity and material does not build up on the bulbs so that killing of viruses and bacteria occurs before disposal of the wastewater into the final effluent stream so that it remains protective of human contact in the future use of this wastewater. Some of the key design considerations for a disinfection system include ease of maintenance, having a way to change bulbs easily for operators, also having redundancy such that having sufficient number of bulbs and UV systems, should that one go down, there's plenty of UV disinfection potential available, as well as safety, making sure that the operators are shielded from the UV rays. And this is one of the advantages of UV over chlorine, is that it's also a much safer technology to use for operators rather than chlorine gas disinfection, which was historically used in the past. You can see here our final effluent outfall. One of the key components of an outfall is typically to provide a little additional aeration of the water before introduction into the receiving stream. You can see our facility uses a cascade design to oxygenate the water. We remain very proud of our effluent quality. As you can see here, this water is equally clear as the receiving stream water. And one of our goals is to protect the environment and provide an effluent that is better and cleaner than the water in the normal receiving stream. No wastewater treatment plant would be complete without a proper SCADA system. SCADA stands for Supervisory Control and Data Acquisitions. This is the computer system that allows the operators to interface with each component of the treatment process. Some of the key design considerations for SCADA include cybersecurity, making sure that our system is locked out from outside influences that may want to create harm or do damage to our treatment process. Usability. We want to make sure that operators can easily interface with this, and you can see that we've constructed this to look exactly like our wastewater treatment plant. Alarm notifications. We want to make sure that operators are easily notified of alarm conditions and that the alarm conditions can be set by senior personnel so that everyone knows if it's a very important alarm or not. Also, storage of process information is another key component of any system. We want to make sure that we're logging all of the flow data and all the process control data in the system for future use and evaluation by operators as they adjust treatment processes. Finally, we want it to be intuitive. We want the operator interface to be easy to use and understand so that the operators are comfortable using it no matter what. Our system is able to be used in phones remotely as well as here in the plant itself. A key component of any wastewater treatment plant design is to understand the human factor. The fact that human beings are going to be here day in and day out operating this facility, 24 hours a day, 7 days a week, 365 days a year. As a result, we want to design a facility in a manner that makes their jobs easy, comfortable, and efficient. A key consideration in the wastewater treatment plant design is the laboratory. Decisions need to be made early on in the design process with regard to what analytical processes is this lab going to be able to conduct. In our facility, we're able to conduct nearly all processes required to meet our NPDES permit, with the exception of metals analysis. In our lab here, you'll see we have stations set up for chemical biological oxygen demand, phosphorus measurements, ammonia measurements, pH measurements, as well as key process data such as volatile suspended solids, mixed liquor suspended solids concentrations, and settleability. And thinking of the human aspect of a wastewater treatment plant, it's important to also consider workspace, creature comforts, and equipment material storage as part of the overall treatment process. Workspace is key for operators to have room to view their SCADA screens, research where to buy replacement materials, as well as do such little tasks such as timesheets or write short memos. Creature comforts are important too. Wastewater being a dirty business, we provided laundry facilities for our staff, showers, lockers, and a lunchroom to try to make their jobs as easy as possible and as comfortable as possible, considering the difficult nature of the work that they conduct. Finally, it's very important to consider equipment and material storage. You want to have sufficient space to store replacement materials, especially as our supply chain difficulties increase day in and day out. There's a large amount of equipment that also gets used for wastewater treatment, and you want to make sure you build storage for that, such as a Vector truck for cleaning pump stations and sanitary sewers, material handling equipment, such as a Manitou for handling residuals in the facility, as well as such things such as lawnmowers, pumps, pressure washers, and other equipment that's necessary to keep the plant clean and spotless. We thank you for joining us on our facility tour. We hope we've highlighted some of the key considerations as you look at designing wastewater treatment plants for the future, and we hope that you're able to join us at the Genoa-Oceola Wastewater Treatment Plant facility again in the future.